Induction to prove first-order recursive formula. So a recursive formula is defined by one or more preceding terms. And we can have two definitions for a recursive formula. We can have a recursive definition, or we can have a closed form definition. And we're going to look at an example, and we want to prove with mathematical induction that u to the n equals 6 times u to the n minus 1 minus 5 times u to the n minus 2, where u1 equals 2, u2 equals 6. We want to prove that it equals u to the un equals 5 to the n minus 1 plus 1 for all values where n is greater than or equal to 1. Now the reason I brought up the example now is to just show the difference between the recursive definition and the closed form definition. So the recursive definition is dependent on the terms before your term. So you can see here, this is the recursive definition because un is dependent on the term before it and the term before that. And this is the closed form definition because this doesn't depend on any of the terms, it just depends on a value of n. So if you wanted the fifth term, you could just plug in n equals 5. But if you wanted the fifth term with the recursive definition, you'd need to know the fourth term and the third term to do so. So here we're looking at proving with mathematical induction that the recursive definition equals the closed form definition. So how are we going to do that? So the first thing we need to do is show that it's true for the base case where n equals 1. Let's have a look when n equals 1. So when n equals 1, we're going to look at u1 equaling 5 to the 1 minus 1 plus 1, and we're going to get 5 to the 0, which is 1, so we're going to get 1 plus 1, which is 2, and we've already been told that u1 equals 2, so that's true. Now we're going to assume that these definitions are true. We're going to assume true for values of n that are between 1 and k. And let's write some down. So we're assuming that the closed form is true. So of course we're trying to prove that the closed form equals the recursive definition. So let's write some of those down. So we'll get u to the 1 is going to be 5 to the 1 minus 1 plus 1. U to the 2 will be 5 to the 2 minus 1 plus 1. Now we usually jump ahead here and write the kth term, but we're going to write the one before it. So we're going to write u of k minus 1. That's going to be 5 to the k minus 1 minus 1. So we're going to get 5 to the k minus 2 plus 1. Then we're going to get uk, which is going to be 5 to the k minus 1 plus 1. So we're going to assume that that closed form definition is correct for a value of n equals k. Now we're going to prove true for n equals k plus 1. So we're going to take our recursive definition and sub in n equals k plus 1. So we're going to get u of k plus 1 equals 6 times u of k plus 1 minus 1, so we're going to get UK, minus 5 times u of k plus 1 minus 2, so we're going to get k minus 1. Now we have expressions for u to the k and uk minus 1, so we're going to get 6 times our definition for uk is down here. So we get 6 times 5 to the k minus 1 plus 1, minus 5 times our definition for uk minus 1, which is here. So we get 5 to the k minus 2 plus 1. And let's expand this out. So we get 6 times 5 to the k times 5 to the minus 1. So we're just splitting up all our indices. Plus 6 minus 5 times 5 to the k times 5 to the minus 2 minus 5. Now, what we want to do here we want to, over here, we've got 5 times 5 to the minus 2. We can actually, these have the same base, so we can add their powers together. So we have 6 times 5 to the k times 5 to the minus 1 plus 6 minus 5 to the k. Now, the 5 times 5 to the minus 2 gives us 5 to the minus 1 minus 5. What we can do is we can actually let's let x equal 5 to the k times 5 to the minus 1, just so we can see things a little clearer. So that is happening here and here. So this is going to give us 6x minus x, and then 6 minus 5 is just 1. So 6x minus x is 5x plus 1, and let's just put it back in. This just was to help us visualize those like terms. So we're going to get 5 times x, which we know is 5 to the k, times 5 to the minus 1 plus 1. That should be minus 1. Then 5 times 5 to the minus 1, simplify to 1, and we're left with 5 to the k plus 1 equals u to the k plus 1. But we want to show that it equals this form. For the closed form definition, that's just of u to the n. So what we can do is we can just let k plus 1 equal to n, which implies that k equals n minus 1. So subbing that in, we get u to the n equals 5. We know k is equal to n minus 1 plus 1, and that equals our closed form definition, and we've successfully shown that it must be true by mathematical induction.